Welcome to this video on solving systems of equations that have either no solution or infinitely many solutions. Let's take a look at one that has infinitely many solutions. You wouldn't know that by just looking at it, so you would just go about the business of solving a system like you normally would. Here I might recommend, for example, taking the first two equations, multiplying one of them by -1 so that you could add and cancel the x's. You'll recall that a good strategy here is to cancel the same variable twice. For this particular equation, I noticed all the coefficients were divisible by 4, so I multiplied the whole equation by 1/4. But now that I've canceled x one way, it would benefit me to cancel that same variable, x, another way. So I'll take the bottom two equations, multiply one of them by -1, thereby creating a situation where if I add the equations, the x's will cancel again, leaving me with a y and z equation. I happen to notice that this equation that each coefficient was divisible by 8, so I multiplied the whole equation by 1/8, and I got this. Here's an interesting fact. If you ever get the same equation two different ways, that's an indication that the system has infinitely many solutions. That means that, for example, 3,1 would be a solution to both of these. 0,4 would be a solution to both of these. Here's another solution to both, and you can see, even with decimals, there's infinitely many solutions to this system of equations because they're both the same equation. So when you know that your system's going to have infinitely many solutions, what you do is just understand that either variable can be any number. I'm going to write the symbol y equals heart to represent that y could be anything. I want you to imagine that there could be any number where that heart is. Whatever number y was, couldn't we plug that in and then solve for z? Wouldn't z have to be 4 minus that number? So in some sense, I've solved for y and z here, not numerically, but I've solved for y by declaring that it can be any number, and I've solved for z by saying that z would equal 4 minus that number. So that only leaves us having to solve for x. So I brought one of the equations down, wouldn't matter which one, and I plugged in what I so far have determined, which is that y can be any number, and that z would have to be 4 minus that number. And I can now solve this equation for x in terms of this any number symbol, the heart that I've chosen. I could combine like terms, treating the heart algebraically, add some terms to the other side and combine like terms again. And now I've effectively solved for x, not numerically, but in the sense that x will be something in terms of whatever number y happens to be. Now all these hearts are kind of silly looking in a math class, so let me change them all to just a letter. But I want you to know there's nothing special about the letter K. It's just a letter I chose to represent the fact that y can be any number. And now, in some sense, in some infinite sense anyways, I've solved for x, y, and z. I can now take those answers, put them in an ordered triple, and I've now found all infinitely many answers to this problem with the understanding that k could be any number. Put the original problem back. Here's the answer we got to that problem. Even though I'm done solving this infinitely many solutions problem, I'd like to talk a little bit about what it means for k to be any number. I took a random number for k, plugged it into the solution, got an answer. That thing in purple there at the bottom is a solution to the original system. Here's another number for k, plugged it in, worked it out. I've now created another answer for k, for this system of equations. And I'm just picking random numbers for k here. Nothing special about 6, but when I plug 6 in for all the k's, the ordered triple I get is a solution to the original system. I've shown 3 of them here just to prove a point, that this system does in fact have infinitely many solutions, and these 3 in purple here are specific solutions out of that list of infinitely many. One other thing to note is that sometimes instead of a fourth letter in the problem, this K that I've created to represent Y, you'll see people just, instead of saying that Y could be anything and calling it K, just calling it Y in the first place. So you may see that instead. I'll put the K's back. And one other thing worth mentioning here is that this is not the only way to go about solving the problem. Remember when we had this equation and I declared that Y could be any number? I could have just as easily declared Z could be any number and replaced Z with K instead of Y. Now I didn't show all of the algebra here, but I worked that out on scratch paper. The end result of that work is that I got a different looking answer. But this answer is the same as the one above it because they both represent the same infinite set of ordered triples. I also worked it out in a totally different way. This strange answer you're looking at here came from the result of the following. Instead of canceling X out in the original problem, I canceled Y. I solved the problem a completely different way and got the answer here where the K, or the parameter, so to speak, is in the X slot instead of the Y or Z slot like it is above. You're not supposed to follow all of this algebra here. The only point I want to make is that these infinite sets can be represented in many different ways, and you're looking at three of them right here. All of these three answers represent the same infinite set of ordered triples. Let's take a look at a system of equations that has no solution at all. Now, you wouldn't know it has no solution by looking at it, and so let's just go about the business of solving this system as if we didn't know it had no solution. I would take the top two equations in an effort to cancel X, multiply one of them by -1, thereby canceling the X and creating an equation. I like to cancel the same variable twice, so I would probably take these two and do the same thing, multiply by a -1 in order to get the X's to cancel in this case. Now, normally when we get down to this point, we solve the system of equations that is created by these two steps. I don't know if it occurs to you here, but these equations are in contradiction to one another. Some people can look at this and instantly see that there's no way there could be numbers Y and Z that would make both of these true. If you happen to be that kind of person, then you're done with this problem. It has no solution. Many students can't see by looking at these that there are no solutions, so you'll discover it when you go about the business of solving. Let's pretend we didn't know this was a no solution problem, and we were just trying to solve for Y and Z. I would probably multiply by -2 in an effort to cancel out the Y's. But in an effort to cancel out the Y's, I've also canceled out the Z's. This entire addition of two equations results in what's called an absurdity in mathematics. Something is said to be absurd if it can never be true. 0 = 1 can never be true and is definitely an absurdity. When your equations reduce down to a false statement like this, that is an indication that it has no solution. And if that 2x2 system has no solution, then so too does the original system in this problem.